Okay, good afternoon students. So in the last class we have discussed about silicon control rectifier and DIAC. Okay. So what is SCR? So SCR is a 4-layer 3-terminal device. So in which the end P layer acts as anode, the end N layer acts as cathode, and P layer nearer to cathode acts as gate. Okay, SCR is a 4-layer 3-terminal device. So the 3 terminals are anode, cathode and gate. So actually the leakage current in silicon, it is very small compared to germanium. So SCRs are made of silicon and not germanium due to the leakage, very low leakage current. Okay, so SCRs are made with silicon due to the low leakage currents. Okay, so SCR is a 4-layer 3-terminal device. So in which the NP layer acts as anode, the N layer acts as cathode, and the P layer nearer to cathode acts as gate. SCR acts as a switch when it is operated in the forward bias. So SCR acts as a switch when it is operated in the forward bias. So when the gate is kept open, so that is the gate current Ig equal to 0. If Ig equal to 0, so that means when gate is open. So operation of SCR is similar to PNP diode. When the gate current is 0, the operation of SCR is similar to PNP diode. Okay. So when Ig is less than 0, so the amount of reverse bias applied to junction J2 is increased. So the breakover voltage VBO is increased. Okay. So when Ig is greater than 0, the amount of reverse bias applied to J2 is decreased. So thereby decreasing the breakover voltage. So with very large positive gate current, breakover may occur at a very low voltage. So that's why the characteristics of SCR is similar to the ordinary PN diode. Once SCR is turned on, the gate loses the control. That is, the gate cannot be used to switch the device off. Okay. So if once the SCR is going to on state, the gate loses the complete control. So that is, the gate cannot be used to switch the device off, right? So only one way to turn the device off, so to turn the device off is by lowering the anode current below the holding current. Okay, I am explaining about SCR working, right? So to turn on the SCR off, so by lowering the anode current below the holding current. Okay, so if you decrease the anode current below the holding current, then SCR may go to off state. So by reducing the supply voltage below the holding voltage. So SCRs are used in relay control, motor control, phase control, heater control, so battery charges, inverters, regulated power supplies. Okay. So these are the applications of SCR. SCRs are used in relay control, motor control, phase control, heater control, battery controls, battery charges, inverters and regulated power supplies. Okay. See here, so we have the two definitions in the SCR operation. So latching current, holding current, right? So we have discussed in the last class. So what is latching current? So the latching current is the minimum current required to trigger the device from its off state to its on state. Okay. So latching current is the minimum current required, so to trigger the device from its off state to on state. So to change the condition of the SCR from off state to on state, so latching current is the minimum current. Okay. So next, what is the holding current? Holding current is the minimum value of current to hold the device in on state. So holding current is the minimum current to hold the device in on state. So for turning the device off, the anode current should be lowered below holding current, So by increasing the external circuit resistance. Okay. So this is about latching current and holding current. So today we will see, so what is a TRIAC? Okay. So we will see the characteristics of VA characteristics of TRIAC and the working of TRIAC, all these things. See here, the major drawback of an SCR, is it conducts current in only one direction. So SCR conducts only in one direction. So AC system is necessary to control both positive and negative half cycle. Right? So for this purpose, a semiconductor device called TRIAC is used. So TRIAC is a combination of two SCRs connected anti-parallel. Okay. So the drawback of an SCR, so the SCR conducts only in one direction, but the AC system is necessary to control both positive and negative half cycles. So for this purpose, a semiconductor device called TRIAC is used. Okay. So what is TRIAC? A triode for alternating current. This is also called bidirectional triode thyristor or bilateral triode thyristor. Okay. So it is a 3-terminal electronic component that conducts current in either direction when triggered. So it conducts the current in two directions. Okay. So TRIAC is a 3-terminal AC switch. So it is different from the silicon controlled rectifiers. So SCR conducts in only one direction, but the TRIAC can conduct in both the directions. Okay. So SCR conducts in both the directions, that is whether the applied gate signal is positive or negative. So if the applied gate signal is positive or negative, the SCR will conduct. So this device can be used for AC systems as a switch. So TRIAC can be used for AC systems as a switch. So it is a 3-terminal 4-layer bidirectional semiconductor device. TRIAC is a 3-terminal 4-layer bidirectional semiconductor device. So that controls the AC power. Okay. So the maximum rating of TRIAC, it is 16 kilowatt. It is available in the market. So when it comes to the construction of TRIAC, see here. So two SCRs are connected in inverse parallel with the gate terminal as common. That means the two SCRs are connected in anti-parallel connection, right? So then the TRIAC is formed. If you connect the two SCRs in anti-parallel connection, then the TRIAC is formed. So gate terminal is connected to both the N and P regions. See here. Here the gate terminal is connected to both the N and P regions, due to which gate signal may be applied, which is irrespective of the polarity of the signal. So here we don't have any cathode, we don't have any anode. Okay. Because it conducts in both the directions. So we don't have any anode and cathode. So it works for both the polarities. It works for both the polarities. So that means the device is bilateral. So it consists of 3 terminals. So namely MT1, MT2 and gate. So main terminal MT1 means, see here, the 3 terminals of TRIAC are MT1, MT2 and gate. So main terminal 1 main terminal 2 and gate. Okay, so it conducts in both the directions, so there is no anode and cathode. Okay, so it consists of MT1 and MT2. So main terminal 1, main terminal 2 and gate terminal, right? So it consists of, see here, it is the basic structure of the track, the basic structure of track. So it is PN. Okay. So the track can be turned on by applying the gate voltage. The track, okay, see here. So it consists of 4 layers, 3 terminals. The gate terminal is nearer to the MT1 terminal. The terminal MT1 makes contact with layers N2 and P2. So the terminal MT2 makes a contact with layers P1 and N4. So if you check the basic structure, so then you can find out the terminal T1 makes contact with layers N2 and P2. The terminal T2 makes contact with layers P1 and N4, right? So the gate terminal makes contact with layers N3 and P2. The gate terminal makes the contact with the layers N3 and P2. Okay, so it has 4 layers, right? So these are the VI characteristics of the track. So if you see the working, the track can be turned on by applying the gate voltage higher the breakover voltage. Okay, so the track can be turned on by applying the gate voltage higher than the breakover voltage. So the gate voltage must be greater than the breakover voltage. So without making the voltage high, it can be turned on by applying the gate pulse of 35 microseconds. Gate pulse of 35 microseconds, right? So when the voltage applied is less than the breakover voltage, we use gate triggering method to turn on the triac, right? So if you want to turn on the track, apply the gate voltage greater than the breakover voltage, right? So in other way, when the voltage applied is less than the breakover voltage, we use gate triggering to turn on the track. Right? So there are 4 different modes of operation. So first one is, so if we check the basic structure, when MT2 and gate being positive with respect to MT1, when MT2 main terminal 2 and gate being positive with respect to MT1, then the current flows through the path P1 N1 P2 N2. Okay, so here P1 N1 and P2 N2 are forward biased, but N1 P2 is reverse biased. Okay, see here, when MT2 and gate, so being positive with respect to MT1, then the current flows through the path P1 N1 P2 N2, right? So here P1 N1 and P2 N2 are forward biased, but N1 P2 is reverse biased. Okay, so then the track is said to be operated in positively biased region. So positive gate with respect to MT1 forward biases P2N2, forward biases P2N2 and breakdown occurs. The positive gate with respect to MT1. The positive gate with respect to MT1, forward biases P2N2 layers and the breakdown happens and the breakdown occurs, right? In the second case, when MT2 is positive, but gate is negative with respect to MT1. When MT2 is positive, but gate is negative with respect to MT1. Okay? The current flows through the path P1N1, P2N2. But P2N3 is forward biased and current carries injected into P2 on the track. So that is the second case. In the third case, when MT2 and gate are negative with respect to MT1, current flows through the path P2N1, P1N4. So two junctions P2N1 and P1N4 are forward biased. So but the junction N1 P1 is reverse biased. So the track is said to be in the negatively biased region. Okay. So in the fourth case, when MT2 is negative but gate is positive with respect to MT1, when MT2 is negative but gate is positive with respect to MT1, P2N2 is forward biased at that condition. So current carriers are injected, then the track turns on. Okay. So these are the four modes of operation in the track. So if we see the advantage, so it can be triggered with positive or negative polarity of gate pulses. So the track can be triggered with positive or negative polarities of the gate pulses. So it requires only a single heat sink. So in the SCR requires two heat sinks. Okay, track requires only single heat sink, and it requires single fuse for the protection. So these are the advantages of the track. So when it comes to drawbacks, so the tracks are not much reliable compared to SCR. Tracks are not much reliable compared to SCR. So lower ratings are available compared to SCR. Okay. So when it comes to uses, so these are used in control circuits. So tracks are used in control circuits. So it is used in high power lamp switching. It is used in AC power controls. Okay. So these are the applications. So temperature control, liquid level control, phase control. So speed control of single phase induction motors as well as series motors and power switches, right? So these are the applications of track. So next we will see about Varactor diode. So what is a Varactor diode? As the name implies, so Varactor diode, variable capacitor. See here the basic structure and the symbol of the Varactor diode. So it is also called varicap. So one second. So the Varactor diode is also called as varicap or voltage variable capacitor diode. See here. So when any diode is reverse biased, a depletion region is formed, right? So if you take PN junction diode, if it is operated in reverse biased condition, a depletion region is formed. Okay. So if you apply the larger reverse bias, if you apply the larger reverse voltage across the diode, then the width of the depletion layer increases. Okay, if you apply the larger reverse voltage across the diode, the width of the depletion region increases. So the width of the depletion region becomes wider. If you decrease the reverse bias voltage, the depletion region width decreases, right? So if you decrease the reverse bias voltage, then the depletion region width also decreases. One second. One second, somebody are changing the slides. So actually this depletion region acts as an insulator. The depletion region acts as a insulator. So it prevents the conduction between the N and P regions. It prevents the conduction between the N and P regions. So it separates the depletion region separates the two plates of a capacitor. So just like a dielectric, it separates the two plates of a capacitor. So here, so we can write CT, so is directly proportional to 1 by W. Okay. So if the capacitance here, the capacitance is inversely proportional to the distance between the plates. The capacitance is inversely proportional to the distance between the plates. So here CT is the transition capacitance. So here the transition capacitance varies inversely with the reverse voltage. The transition capacitance varies inversely with the reverse voltage, right? So Varactor diode is also called varicap. So our voltage variable capacitor. So here the diode is operated under reverse bias conditions. The diode is operated under reverse biased conditions. So around the junction in the depletion region, where no current carriers are available, so as a result current can be carried in the P and N regions, but the depletion region is an insulator. So depletion region acts as an insulator, right? So actually this is the same construction as in the capacitor. So it has the conductive plate separated by insulating dielectric. The capacitance depends on a number of factors, that is plate area, dielectric constant of the insulator between the plates, and the distance between the two plates. So here similarly it looks like a capacitor. Okay. So the capacitance of a capacitor is dependent on different factors. So first one is plate area and the dielectric constant of the insulator between the plates and the distance between the two plates. So see here, so in the Varactor diode, So it is possible to increase and decrease the width of the depletion region by changing the level of the reverse bias. So if you change the reverse bias voltage, so the depletion region width can be changed. If you see the characteristics, see here. So these are the characteristics of the Varactor diode. So x-axis is the reverse bias voltage, and y-axis is the transition capacitance. So at 0 voltage, so the Varactor depletion region width is small and the capacitance is large. So approximately it is 600 picofarads, right? So at 0 voltage, the Varactor depletion region width is small, the capacitor and the capacitance is large. See here, see in the characteristics, right? At 0 voltage the capacitance is maximum, that is approximately 600 picofarads. When the reverse bias voltage increases, so across the Varactor, the capacitance is going to decrease. So nearly it is 30 picofarads. So the Varactor diodes are used in one second. So the Varactor diodes are used in FM radio and TV receivers. So Varactor diodes are used in FM radio and TV receivers. So these are the applications of the Varactor diode. Automatic frequency control in RF filters and voltage controlled oscillators. Okay, so these are the applications of Varactor diode. So next we will discuss about Schottky Barrier diode or hot carrier diode. So the other name for Schottky Barrier diode is hot carrier diode. Okay, so see the construction of Schottky Barrier diode. So this construction is different from the conventional PN junction. See here it has silicon dioxide screen, so metals, gold leaf metal contact, so metal semiconductor junction. Okay, so it is quite different from the conventional PN junction. So Schottky Schottky Barrier diode is an extension of the oldest semiconductor device, that is a point contact diode, right? So it is the extension of the oldest semiconductor device, point contact diode. Here the metal semiconductor interface is surface. Here the metal semiconductor interface is a surface. So the Schottky barrier rather than a point contact. The Schottky diode is formed when a metal such as aluminum is brought into contact with a moderately doped n-type semiconductor, and it is a unipolar device. The Schottky barrier diode is a unipolar device. So because it has electrons as majority carriers on both sides of the junction, so it is a unipolar device. So here the electrons are the majority carriers on both sides of the junction. So there is no depletion layer formed near the junction. Okay, so here only majority carriers are there, so there is no depletion layer is formed. But in the PN junction diode we have the depletion layer. So the construction is different from the PN junction diode. There is no depletion layer formed near the junction, right? So here the delay present in the junction diode, so due to hole electron recombination time. So actually in the PN junction diode the delay is present. The delay is present, right? So due to the hole electron recombination time. But the delay is absent in this Schottky diode. The delay is absent in the Schottky barrier diode. So here, because of the large contact area between the metal and semiconductor, the forward resistance is low. The forward resistance is low. So because of the large contact area between the metal and semiconductor. So see the symbol. So here in both the materials, the electrons is the majority carrier. So why it is called hot carriers? So since the injected carriers have a very high kinetic energy level compared to the electron of the metal, so they are commonly called hot carriers. So here the forward current is dominated by electron flow from semiconductor to metal, and the reverse current is due to the electron flow from metal to semiconductor. So it is very little minority carrier injection from semiconductor into metal. So Schottky diodes, so that's why the Schottky diodes are said to be majority carrier devices. The Schottky diodes are said to be majority carrier devices. So it is called hot carrier diode because so when it is forward biased, the conduction of electrons on the n side, so it gains sufficient energy. So it gains sufficient energy to cross the junction and enter into the metal. Okay. So these are the PN junction diode characteristics and Schottky diode characteristics. So compare this PN junction diode characteristics and Schottky diode characteristics. So Schottky diodes, this can be used for frequencies more than 300 MHz. So it is commonly used in switching power supplies at frequencies of 20 GHz. So on the noise levels are low. Here the noise levels are low. And it is also used in clipping and clamping circuits. Okay, so these are the applications of Schottky barrier diodes. So with this, I am going to stop the presentation. If you have any doubts, you can ask.